Imagine you have two coins. You flip them in separate rooms, miles apart, with no possible way for one to influence the other. And yet, every single time, without fail, they land on matching sides. Not half the time, not most of the time, every time. You would say that is impossible. You would say someone rigged the coins, or there is a hidden signal, or the whole thing is a trick. But here is what makes quantum entanglement so disturbing. Physicists have tested exactly this kind of scenario with real quantum particles, separated by enormous distances, with every known form of communication ruled out. The correlations are real. And after nearly a century of trying, no one has found a classical explanation that works. The universe does something here that should not be possible. Tonight, we are going to understand why. If you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It is a small thing, but it means a lot. Now, let's begin. Let's start with something you already know, something so obvious you have never had to think about it. If two objects are physically separated, sitting in different rooms with no wire between them, no radio link, no connection of any kind, then what happens to one should have absolutely nothing to do with what happens to the other. You knock a glass off the table in your kitchen, and a glass on a shelf in a house across town does not suddenly fall. You flip a light switch in your living room, and a lamp in a stranger's apartment does not turn on. This is not a law you were taught. It is something far deeper. It is built into the way you understand reality. Separate things behave separately. Independent objects produce independent results. This principle is so natural that you would never bother stating it out loud. It would be like announcing that rocks are hard or that the floor is below the ceiling. It is just how the world works. It is how the world has always worked as far as everyday experience is concerned. And if someone told you they had two coins, one in Paris and one in Tokyo, and that every time they flipped those coins simultaneously, the results matched, you would not be impressed by the physics. You would look for the trick. Maybe the coins are weighted. Maybe someone is signaling between the two rooms. Maybe the flips are coordinated in advance. There must be some explanation rooted in ordinary cause and effect, some physical mechanism linking the outcomes. Because if there is no link, no shared history, no signal, and no prearrangement, then perfect correlation between distant random events is not mysterious. It is impossible. This is the starting point. This is the intuition you need to hold firmly in your mind, because quantum entanglement is going to challenge it directly. Not with philosophy, not with speculation, with experimental facts so well established that no serious physicist disputes them. The correlations are real. They have been measured thousands of times in laboratories around the world, under conditions so carefully controlled that every ordinary explanation has been systematically eliminated. And what makes entanglement so deeply strange is not that the correlations exist. It is that no classical picture of independent objects carrying independent properties can reproduce them. To understand what is happening, we need to set up the experiment. And the experiment, at its core, is remarkably simple. You start with a source, some physical process that produces two particles at the same time. These could be photons, which are particles of light. They could be electrons or atoms. The specific type of particle does not matter for the basic logic. What matters is that the source produces two particles in a very specific way, a way that ties their quantum descriptions together from the very beginning. Here is a concrete example. Certain crystals, when hit by a laser beam, can split a single incoming photon into two outgoing photons. This process is called spontaneous parametric down conversion. The two photons fly off in different directions, and because of how the process works, their polarizations are linked. But why are they linked? Why does this process create entanglement rather than just producing two ordinary independent photons that happen to fly off in different directions? The answer lies in conservation laws. Physics demands that certain quantities be conserved, meaning the total amount before and after any process must remain the same. Energy must be conserved, momentum must be conserved, and in this case, a property related to polarization must be conserved. The incoming photon from the laser has a specific energy and a specific polarization. When the crystal splits it into two outgoing photons, the total energy of the two new photons must equal the energy of the original. The total momentum must be conserved, and the polarization states of the two outgoing photons must be related in a way that is consistent with the symmetry of the original photon and the crystal. The physics of the interaction demands a specific relationship between the two outgoing photons. It does not determine the polarization of either one individually. It determines only the relationship between them. This is the crucial point. The crystal does not produce one photon with vertical polarization and one with horizontal polarization. It does not assign definite polarizations to either photon. Instead, it produces a pair whose polarizations are constrained to satisfy a conservation law without specifying which photon gets which value. The result is a quantum state that says something very precise about the pair, about how the two polarizations relate to each other, while saying nothing definite about either photon individually. It is a bit like a process that always produces exactly one red ball and one blue ball, but never decides which ball is which until someone opens the box. Except that analogy is not quite right, because in the classical version, the balls have definite colors inside the box, and you simply do not know which is which. In the quantum version, the colors genuinely do not exist until someone looks. The only thing that exists before measurement is the relationship. One will be red and one will be blue, but neither is anything definite on its own. This is how nature creates entanglement, not by assigning matching properties to two particles and sending them on their way, the way you might hand two friends identical sealed envelopes, but by creating a situation where the laws of physics constrain the relationship between two particles without determining the individual properties of either one. The relationship is real and precise. The individual properties are not. And that distinction between a definite relationship and indefinite individuals is the heart of what makes entanglement so different from any classical correlation. Polarization is a property of light related to the direction in which the light wave oscillates. You can think of it loosely as the orientation of the photon's vibration. When you send light through a polarizing filter, like the lenses in polarized sunglasses, the filter either lets the photon through or blocks it, depending on the photon's polarization relative to the filter's angle. So you have two photons produced together. One flies to the left, one flies to the right. You let them travel. They move apart at the speed of light, getting farther and farther from each other. Eventually, one photon arrives at a detector on the left side of the laboratory, maybe held by an experimenter named Alice. The other photon arrives at a detector on the right side, maybe held by an experimenter named Bob. Alice and Bob can be in the same room, or they can be in different buildings. They can be separated by meters, by kilometers, or in principle by any distance at all. The experiment has been performed with photons separated by more than 1,200 kilometers using a Chinese satellite called Meteus, launched in 2016. The photons are far apart. There is no physical connection between them, no wire, no beam, nothing linking Alice's photon to Bob's. Alice chooses to measure her photon's polarization along some direction. Maybe she sets her polarizing filter to vertical. She gets a result. The photon either passes through the filter, which means it registered as vertically polarized, or it does not, which means it registered as horizontally polarized. Her result is binary, up or down, pass or block, yes or no. And here is the critical fact. If Alice measures vertical polarization and gets a result, and Bob also measures vertical polarization on his photon, their results are perfectly correlated every single time. If Alice's photon passes through a vertical filter, Bob's photon will behave in a precisely corresponding way with certainty. Not most of the time, every time. Now, you might say, fine, so what? Maybe the photons left the source with definite polarizations already decided. Maybe one was vertical and the other was horizontal from the start, and the measurements simply revealed what was already there. This is the most natural classical response, and it is exactly the explanation your intuition wants to grab onto. The photons carried instructions with them. They were programmed at birth, and the measurements just read off those pre-existing programs. This is where we need to pause and talk about what a quantum state actually is. Because the answer to whether the photons had definite polarizations all along is not just unknown. According to quantum mechanics, the answer is no. And this is not a statement about our ignorance, it is a statement about reality itself. In everyday life, when you do not know something, it is because the information exists, but you lack access to it. A coin is in a box. It is either heads or tails. You do not know which, but it is definitely one or the other. Your ignorance does not change the coin. The coin has a definite state regardless of whether you look at it. This is how we naturally think about the world. Objects have properties. Those properties exist whether or not anyone checks. Quantum mechanics says something very different. A quantum particle does not, in general, have a definite value for a property until that property is measured. Before measurement, the particle exists in what physicists call a superposition. This is not a fancy word for uncertainty or ignorance. It is a specific mathematical description in which the particle genuinely does not possess a single definite value for the property in question. The particle's quantum state is a combination of multiple possibilities, and none of those possibilities is more real than the others until a measurement forces a definite outcome. This sounds abstract, so let me make it concrete. Take a single photon traveling through space. You want to know its polarization. Is it vertical or horizontal? Before you measure, quantum mechanics says the photon's state might be an equal superposition of vertical and horizontal. It is not that the photon is secretly vertical and you just have not checked yet. It is not that the photon is secretly horizontal. The photon does not have a definite polarization. It is in a state that includes both possibilities simultaneously, with specific mathematical weights attached to each. When you send this photon through a polarizing filter, the measurement forces a definite result. The photon either passes or does not. At that moment, the superposition collapses to a single outcome. You get vertical or horizontal, and the probability of each outcome is determined by the weights in the superposition. If the superposition was 50-50, you get vertical half the time and horizontal half the time, with no way to predict which you will get on any individual measurement. The randomness is not due to hidden information you are missing, it is fundamental. The universe has not decided yet until the measurement happens. This is already strange, but it is not the strangest part. The strangest part is what happens when you have two particles instead of one. And this is where entanglement enters. When two photons are produced together in the way I described, through that crystal process, they do not leave the source as two independent particles, each carrying its own separate quantum state. They leave as a single quantum system described by one shared state. This shared state cannot be broken into two individual states, one for Alice's photon and one for Bob's. It is genuinely, irreducibly, a property of the pair. Here is what this means in practice. Before any measurement, neither photon has a definite polarization on its own. Alice's photon is not vertical. It is not horizontal. It does not have a polarization. Bob's photon is not vertical. It is not horizontal. It does not have a polarization either. And yet the shared quantum state specifies a precise relationship between them. If you measure both, their results will be correlated with certainty, even though neither individual result is determined in advance. Think about how strange this is. Each photon individually looks completely random. If Alice measures her photon from each of 1,000 separate entangled pairs, she gets vertical half the time and horizontal half the time, with no pattern, no predictability, nothing distinguishing her results from pure coin flips. Bob sees exactly the same thing on his side. Pure randomness, no pattern, no information. But when Alice and Bob come together afterward and compare their lists of results, the two lists are perfectly correlated. Every time Alice got vertical, Bob got the corresponding result. Every time Alice got horizontal, Bob got the corresponding result. The individual results are random, the joint results are perfectly locked together. Neither list on its own contains any hint of this. The correlation is invisible until you compare the two. Now, let me say that more carefully, because it matters. The correlation is not encoded in Alice's results. It is not encoded in Bob's results. It is not traveling between them as a signal. It exists only in the relationship between their results. And this relationship was established not at the moment of measurement, but at the moment the particles were created, encoded in the shared quantum state. This is not how classical objects behave. In the classical world, correlations between distant events always have explanations rooted in one of two things. Either there is a direct causal link, a signal or influence passing from one to the other, or there is a common cause in the past, a shared origin that programmed both outcomes in advance. Think about identical twins who grew up together and make similar choices. Their correlation comes from shared genetics and shared upbringing. It comes from their common origin. Think about two phones ringing at the same time because someone triggered a group call. Their correlation comes from the signal linking them. These are the only two mechanisms the classical world offers for explaining why distant things behave in coordinated ways. Entanglement does not fit neatly into either category. There is no signal passing between the photons. The measurements can be made so quickly and at such great distances that even a signal traveling at the speed of light could not get from one detector to the other in time. And while there is a common origin, the moment when the photons were created together, the correlations are not the kind that a common origin can explain classically. This is the crucial point, and it is what Bell's theorem will make precise shortly. But for now, the key insight is this. The correlations produced by entangled particles are stronger and more structured than anything that pre-programmed instructions could generate. They are not just unlikely to arise from hidden instructions, they are mathematically impossible to reproduce that way under certain measurement conditions. Let me try to give you a sense of why this is so disturbing from a classical perspective. Imagine you run a company that sells pairs of magic boxes. Each pair is prepared in your factory. You do whatever you want to the boxes before shipping them. Program them, load them with batteries, install tiny computers inside, anything you like. Then you send one box to Alice and one box to Bob. Alice and Bob are in different cities. They cannot communicate with each other during the experiment. Each box has 3 buttons labelled 1, 2, and 3. When you press a button, the box flashes either red or green. Alice presses a button on her box. She sees a colour. Bob presses a button on his box. He sees a colour. They record their results and later compare. Here is what your boxes need to do. Whenever Alice and Bob happen to press the same button, the same number, their boxes must always flash the same colour. If they both press button 1, both boxes flash red or both flash green. Always matching, no exceptions. You might think this is easy. Just program each pair of boxes at the factory. Before shipping, decide what each button will produce. Box A, button 1 gives red, button 2 gives green, button 3 gives red. Box B gets the same program. Button 1 red, button 2 green, button 3 red. Done. When they press the same button, they get the same colour. This is the hidden variable strategy. The boxes carry preset instructions. The correlations come from shared programming at the common origin, and for same button presses, this works perfectly. You can always reproduce perfect same button matching with pre-programmed boxes. But here is where quantum mechanics makes an additional demand. When Alice and Bob press different buttons, quantum mechanics predicts specific statistical patterns in their results. Not perfect matching, but a particular distribution, a particular rate of agreement and disagreement that depends on which buttons they each pressed. And Bell's analysis, which we will explore soon, shows that no possible pre-programming scheme, no set of instructions you could load into those boxes at the factory, can reproduce the statistics quantum mechanics predicts for different button presses, while also maintaining perfect matching for same button presses. The boxes cannot do it. No matter how clever your programming, no matter how complex the instructions you embed, the classical strategy falls short. There are combinations of measurement settings where the observed correlations exceed what any pre-programmed system can produce. This is not a minor discrepancy. It is a clean mathematical boundary, and quantum entanglement crosses it. Let me walk through this with actual numbers so you can feel it rather than just hear it. Suppose Alice and Bob each choose between 3 measurement directions. Call them direction 1, direction 2, and direction 3. These directions are separated by 120 degrees from each other, spread evenly around a circle, like the hands of a clock at 4, 8, and 12. Now imagine programming the boxes at the factory. Each box needs an instruction for each button: red or green for button 1, red or green for button 2, red or green for button 3. Both boxes in a pair get identical programs, so that when Alice and Bob press the same button, they always get matching colors. How many possible programs exist? Each button has 2 options, red or green, and there are 3 buttons. So there are 2 times 2 times 2, which equals 8 possible programs. Let me list them. A box could be programmed red, 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 or red, red, green, or red, green, red, or red, green, green, or green, red, red, or green, red, green, or green, green, red, or green, green, green. Those are the only 8 possibilities. Every pair of boxes must use one of these 8 programs. Now, what happens when Alice and Bob press different buttons? Take the program red, red, green. If Alice presses button 1 and Bob presses button 2, Alice gets red and Bob gets red. They match. If Alice presses button 1 and Bob presses button 3, Alice gets red and Bob gets green. They do not match. If Alice presses button 2 and Bob presses button 3, Alice gets red and Bob gets green. They do not match. So for this particular program, out of the 3 possible different button combinations, 1 gives a match and 2 give mismatches. The matching rate for different buttons is 1 out of 3, roughly 33%. Now check another program. Red, green, red. Alice presses 1, Bob presses 2. Red versus green. No match. Alice presses 1, Bob presses 3. Red versus red. Match. Alice presses 2, Bob presses 3. Green versus red. No match. Again, 1 match out of 3. 33%. What about red, red, red? All 3 answers are the same. Alice presses 1, Bob presses 2. Red versus red. Match. Alice presses 1, Bob presses 3. Red versus red. Match. Alice presses 2, Bob presses 3. Red versus red. Match. 3 out of 3, 100% matching. If you systematically check all 8 possible programs, you find that 6 of them give a different button matching rate of exactly 1 out of 3. The remaining 2, red, 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 and green, 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 give 100% matching. No program gives anything in between. The matching rate is either 33% or 100%. Now, the factory might randomly assign different programs to different pairs. Some pairs get red, red, green. Some get green, red, green. Some get red, red, red. If you mix programs randomly across many pairs, the overall different button matching rate becomes a weighted average of 33% and 100%. And any weighted average of 33% and 100% must be at least 33%. There is no way to push it below 33%. That is the flaw. That is the Bell inequality for this setup. Any hidden instruction strategy, no matter how you distribute programs across pairs, must produce a different button matching rate of at least 33%. Quantum mechanics predicts a different button matching rate of 25%. 25%. Below the floor. Below the limit that any possible pre-programmed strategy can achieve. Not by a tiny margin that might be blamed on experimental error, but by 8 percentage points. A clear, measurable, unambiguous violation. And when you perform the experiment with real entangled particles, choosing between 3 measurement angles separated by 120 degrees, the matching rate for different settings is 25%, exactly as quantum mechanics predicts. Below the classical floor, impossible for hidden instructions to reproduce. No matter how you program the boxes, no matter how complicated the instructions, no matter how cleverly you distribute different programs across different pairs, you cannot get below 33%. But nature gets to 25%. The arithmetic is simple. The conclusion is inescapable. The particles are not carrying preset answers. This is why entanglement looks impossible. It is not just that the correlations are surprising. Surprising correlations happen all the time in ordinary life, and we explain them through common causes or signals. It is that the correlations are the wrong kind. They have a structure that cannot be assembled from any combination of pre-existing properties carried independently by the 2 particles. The shared quantum state produces something that separate classical states cannot. And this forces a profound question. If the particles do not carry preset answers and no signal passes between them, then how do they coordinate? How do 2 distant measurements, performed on particles with no definite properties and no communication channel between them, produce results that are perfectly correlated? The honest answer is that quantum mechanics does not explain the mechanism. It does not say how the correlations arise. It simply tells you, with extraordinary precision, what the correlations will be. You set up the experiment. You choose your measurement settings. Quantum mechanics hands you a number, a prediction for the probability of each joint outcome. And when you perform the experiment, those predictions match reality with stunning accuracy. Every single time. No exceptions have ever been found. The theory does not tell a story about signals flying between particles. It does not describe hidden wires or secret communication channels. It simply says, here is the quantum state of the pair, here is what you will observe, and the observations confirm it. This is unsettling because we are used to explanations that tell us why things happen, not just what happens. We want a mechanism. We want a causal story. We want to know what is going on behind the scenes. And quantum mechanics, at least in its standard formulation, refuses to provide one. It gives you predictions. It gives you math. It gives you results that match experiment. But it does not give you a comfortable picture of what is physically happening between the 2 distant detectors when entangled particles are measured. Some people find this liberating. The universe is richer and stranger than our everyday intuitions, and we should update our intuitions rather than insisting the universe behave like a classical machine. Others find it deeply troubling. Albert Einstein was in the second camp. He spent decades arguing that quantum mechanics must be incomplete, that there must be some deeper description of reality that restores the classical picture of objects with definite properties existing independently of observation. He never accepted that nature could be as strange as entanglement implies. And this brings us to the edge of what we can understand without mathematics. We have established what entanglement looks like from the outside. Two particles, no connection, perfect correlations, individual randomness that conceals collective order, a shared quantum state that cannot be decomposed into separate individual states, and a challenge to every classical instinct we carry about how separate objects in separate places should behave. The natural response is Einstein's response. Surely the particles carry hidden instructions. Surely there is some deeper layer of reality where everything makes classical sense. Surely the quantum description is just incomplete, missing variables that, if we knew them, would restore ordinary separateness and predictability. This is a reasonable response. It is perhaps the most reasonable response a thoughtful person could have, and it held sway for decades. The question of whether hidden variables could explain entanglement was considered a matter of philosophical preference rather than experimental science. Some physicists sided with Einstein. Others sided with Niels Bohr, who argued that the quantum description is complete and that asking for more is asking the wrong question. The debate seemed unresolvable. Until 1964, when a physicist named John Bell showed it was not a philosophical question at all. It was a question you could answer with an experiment. And the answer, confirmed by every experiment performed since, was not the one Einstein hoped for. The hidden variable picture does not work. Not because we have not found the right hidden variables yet, but because no hidden variables of the ordinary kind, no preset instructions carried independently by separate particles, can reproduce what entangled particles actually do. The universe does not operate the way classical intuition says it should, and the proof is not theoretical. It is experimental, repeatable, and definitive. That story begins now. So the most natural reaction to entanglement is the one almost everyone has. The particles must carry hidden instructions. They were programmed at the source. Whatever connection they appear to share across great distances was actually established at the moment they were created, and the measurements simply reveal what was already there. This is not a naive response. It is the response of a careful thinker who refuses to accept magic, and for a long time it was the response of Albert Einstein himself. Einstein was not confused about quantum mechanics. He understood the theory deeply. He helped create it. His 1905 paper on the photoelectric effect, showing that light comes in discrete packets of energy called photons, was one of the foundational contributions to quantum physics. He won the Nobel Prize for that work. Einstein was not an outsider criticizing something he did not understand. He was an architect of the building who believed the foundation had cracks. His discomfort centered on a specific issue. Quantum mechanics, in its standard formulation, says that particles do not have definite properties until those properties are measured. A photon does not have a definite polarization before you check. An electron does not have a definite position before you look. These properties come into existence at the moment of measurement. Before that, there is only a quantum state, a mathematical object that gives probabilities for the various possible outcomes you might observe. Einstein found this deeply unsatisfying. He believed physical reality should exist independently of observation. The moon is there whether or not anyone looks at it. A particle has properties whether or not anyone measures them. To Einstein, the idea that measurement creates reality rather than revealing it was not just strange. It was a sign that the theory was missing something. There must be deeper variables, properties the theory does not track, that determine outcomes in advance. Quantum mechanics gives correct predictions, but it is incomplete. It is like a weather forecast that tells you the probability of rain without knowing about atmospheric pressure and humidity. The forecast works, but there is a deeper level of description that makes the probabilities unnecessary. In 1935, Einstein made this argument precise. Working with two younger physicists, Boris Podolsky and Nathan Rosen, he published one of the most famous papers in the history of physics. The paper's title asked whether the quantum mechanical description of physical reality could be considered complete. The argument they laid out became known as the EPR argument, after the initials of the three authors. The EPR argument used entanglement itself as a weapon against quantum mechanics. Here is the logic, stripped to its core. Suppose you have two entangled particles. You send one to Alice and one to Bob. They fly apart, no connection between them. Now Alice measures her particle's polarization along the vertical direction. She gets a result, and because the particles are entangled, she now knows with certainty what Bob's result will be if he also measures vertical polarization. She can predict it with 100% accuracy without touching Bob's particle, without sending a signal, without interacting with his side of the experiment in any way. Einstein then asked a simple question. If Alice can predict Bob's result with certainty without disturbing his particle in any way, does that not mean Bob's particle already had that property before anyone measured it? After all, Alice's measurement happened on her side. It could not possibly have affected Bob's distant particle, especially if they are separated by a large distance and the measurements happen nearly simultaneously. Nothing Alice does can reach Bob faster than light, so whatever Bob's particle is going to show must already be determined. It must be a real property of that particle, existing independently, waiting to be revealed. And this argument applies equally to any measurement direction Alice might choose. She could measure vertical polarization, she could measure horizontal polarization, she could measure at 45 degrees. For each choice, she can predict Bob's corresponding result with certainty. So Bob's particle must have definite values for all these properties simultaneously, just waiting to be uncovered. The quantum mechanical description, which says the particle has no definite polarization before measurement, must be missing something. There must be hidden variables, pre-existing values, that the theory fails to capture. This was Einstein's conclusion. Quantum mechanics is correct in its predictions, but it is not the whole story. A more complete theory would describe these hidden variables and explain the correlations without invoking any mysterious non-local connections. The particles carry their answers with them. The correlations come from their shared past. Everything is local. Everything is real. Everything makes classical sense if you just find the deeper description. It was a powerful argument, clean, logical, and built on principles that seemed impossible to deny. How could you argue against the idea that a property is real if you can predict it with certainty without disturbing the system? How could you argue that Alice's distant measurement somehow creates Bob's result? That would require some kind of instantaneous influence across space, which Einstein's own theory of relativity forbids. Niels Bohr responded to the EPR paper, but his response was philosophical rather than mathematical. He argued that you cannot talk about what properties a particle has independently of how you choose to measure it. The measurement context matters. You cannot separate the particle from the experimental apparatus. This was a valid philosophical position, but it did not settle the debate. For nearly 3 decades after the EPR paper, the question of whether hidden variables could explain entanglement was treated as a matter of interpretation. Some physicists sided with Einstein, others sided with Bohr. Most simply used quantum mechanics without worrying about what it meant. And then John Bell changed everything. John Stuart Bell was a physicist from Northern Ireland who worked at CERN, the European Laboratory for Particle Physics. He was a quiet, thoughtful man who took foundational questions seriously at a time when most physicists considered them irrelevant. He wanted to know whether Einstein was right. Could hidden variables actually reproduce the predictions of quantum mechanics? Was it possible, even in principle, to construct a deeper theory where particles carried definite properties and correlations came from shared instructions rather than mysterious non-local connections? Bell did not answer this question with philosophy. He answered it with mathematics. In 1964, he published a short paper that is now considered one of the most important results in the history of physics. He proved a theorem, and the theorem said something astonishing. Bell showed that any theory satisfying two very reasonable assumptions must obey a specific mathematical constraint on the correlations it can produce between distant measurements. The two assumptions were locality and realism. Locality means that what happens at one location does not instantaneously affect what happens at a distant location. If Alice measures her particle, that measurement does not instantly change anything about Bob's particle far away. Any influence must travel through space at some finite speed, at most the speed of light. Realism means that particles have definite properties whether or not anyone measures them. Bob's photon has a definite polarization before Bob checks. It is a real thing with real attributes, not a cloud of possibilities waiting for observation. These two assumptions together are called local realism, and local realism is exactly what everyday experience teaches us. Objects have properties. Distant events do not affect each other instantly. Local realism is the classical worldview, the worldview Einstein defended. Bell showed that any locally realistic theory, any theory where particles carry predetermined values and no faster-than-light influence exists, must produce correlations that satisfy a specific inequality, a mathematical ceiling, a limit on how strongly correlated the distant measurement results can be. This is called a Bell inequality. The details of the inequality involve probabilities and measurement settings, but the core idea is straightforward. Think back to the magic boxes from earlier. Alice and Bob each have a box with 3 buttons. When they press the same button, their results always match. That is the easy part, and hidden instructions can handle it. But when they press different buttons, hidden instructions impose a constraint on how often their results can agree or disagree. No matter how cleverly you program the boxes, no matter what instructions you embed, the statistics for different button presses must fall within a certain range. Bell proved this rigorously. If the boxes carry preset instructions, there is a limit on the correlations across different measurement settings. You can approach the limit, you can reach it, but you cannot exceed it. The limit is a mathematical consequence of the assumption that the results were determined in advance. And then Bell asked the crucial question: what does quantum mechanics predict? He calculated the correlations for entangled particles measured along different angles, and quantum mechanics predicts that entangled particles violate the Bell inequality. The quantum correlations exceed the classical ceiling, not by a small amount that might be lost in experimental noise, by a significant, measurable margin. Let me give you a sense of what this means in concrete terms. Suppose Alice and Bob each choose between 2 possible measurement settings, setting A or setting B for Alice, setting 1 or setting 2 for Bob. They measure many pairs of entangled photons, randomly choosing their settings for each pair. After collecting thousands of results, they compare their lists and calculate how often their outcomes agree for each combination of settings. A hidden variable theory predicts that a certain quantity constructed from these agreement rates, a specific combination of correlations across the 4 possible setting pairs, must be less than or equal to 2. This is the famous CHSH inequality, named after John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, who formulated this particular version of Bell's inequality in 1969. The number 2 is the classical limit. No pre-programmed system can push it higher. Quantum mechanics predicts a maximum value of roughly 2.828. That is the square root of 8, approximately 41% above the classical limit of 2. And this is not a small technical violation buried in decimal places. It is a large, robust, unmistakable violation. If you perform the experiment and get a value above 2, you have proven that the results cannot come from hidden instructions. No classical scheme can produce that number. In practice, real experiments do not hit the theoretical quantum maximum of 2.828 because no laboratory setup is perfect. Detectors miss some photons. Optical components introduce small errors. Entangled pairs lose quality over distance. But the measured values consistently land around 2.4 to 2.5, well above the classical ceiling of 2 and far too high to be explained by any experimental imperfection. The violation is clean, large, and reproducible. Let me make sure you feel the weight of this. Bell did not just show that one particular hidden variable theory fails. He did not show that some specific model is wrong. He proved that every possible hidden variable theory obeying locality and realism must satisfy the inequality. Every single one. It does not matter how clever the theory is. It does not matter how complicated the hidden variables are. It does not matter how sophisticated the programming. If the particles carry preset answers and no faster-than-light signal links them, the correlations must stay below the classical ceiling. And quantum mechanics says they do not. The universe exceeds the limit. This is what makes Bell's theorem so devastating. It is not an argument against one explanation. It is an argument against an entire category of explanations. It closes the door on every locally realistic, hidden variable theory simultaneously. Not with philosophy, not with opinion, but with a mathematical proof tied to a testable prediction. But a theorem is just mathematics. The universe does not have to obey a theorem. The question was whether actual entangled particles measured in actual laboratories would satisfy the Bell inequality or violate it. Would nature side with Einstein or with quantum mechanics? The first serious experimental test came in 1972. Stuart Friedman and John Clauser, working at the University of California, Berkeley, performed a Bell test using entangled photons produced by calcium atoms. They measured the photons' polarizations at different angles and calculated the relevant correlation. Their result violated the Bell inequality. The quantum prediction won. But the experiment had limitations. There were loopholes, technical gaps that, in principle, allowed a hidden variable advocate to wiggle out. Maybe the detectors were not efficient enough and missed too many photons. Maybe the measurement settings were chosen too slowly, giving the particles time to exchange signals. These loopholes were not plausible to most physicists, but they were logically possible, and science demands rigor. The most famous early experiments were performed by Alain Aspect and his team in Paris in 1982. Aspect's experiments were a major advance because they addressed one of the most important loopholes, the locality loophole. In his experiment, the measurement settings were changed rapidly during the time the photons were in flight. The switch happened so fast that no signal traveling at the speed of light could have carried information about Alice's setting choice to Bob's detector before Bob's measurement was completed. This ruled out the possibility that the particles were somehow communicating. Aspect's results clearly violated the Bell inequality, in agreement with quantum mechanics. The correlations between distant measurements exceeded the classical limit. Pre-programmed hidden variables could not explain what was observed. The violation was statistically significant and reproducible. Over the following decades, experiments became more and more sophisticated. Physicists identified multiple loopholes that could, in principle, allow hidden variable theories to survive, and they systematically closed them. The detection loophole, which involves the possibility that only a biased subset of particles is measured, was addressed by improving detector efficiency. The locality loophole was addressed by increasing the distance between detectors and using faster random setting changes. The freedom of choice loophole, which considers whether the experimenter's setting choices might be influenced by hidden variables, was addressed with increasingly creative methods of generating random settings, including using light from distant quasars billions of light years away to determine which measurements to perform. The landmark year was 2015. 3 separate experiments performed by independent teams in the Netherlands, Austria, and the United States closed all major loopholes simultaneously for the first time. A team in Delft in the Netherlands, led by Ronald Hansen, performed a Bell test using entangled electrons separated by over 1 kilometre. Their detectors were efficient enough to close the detection loophole, their measurements were fast enough to close the locality loophole, and their random number generators were independent enough to close the freedom of choice loophole. The result was a clear violation of the Bell inequality. 2 other teams in Vienna and at the National Institute of Standards and Technology in the United States performed similar loophole-free tests using entangled photons. All 3 got the same answer. The Delft experiment deserves particular attention because of how physically remarkable it was. Ronald Hansen's team entangled 2 electrons that were each trapped inside a tiny diamond crystal. The diamonds were in separate laboratories on the Delft University campus, 1.3 kilometers apart. The electrons were not entangled directly. Instead, each electron was first entangled with a photon emitted from its diamond. The 2 photons were then sent through optical fibers to a station halfway between the 2 laboratories. At that station, the photons were measured together in a way that transferred the entanglement to the electrons. This technique is called entanglement swapping. The 2 electrons, sitting in their separate diamonds over a kilometre apart, had never interacted directly. They became entangled through the photons that acted as intermediaries. Once the electrons were entangled, the team measured their quantum properties. The measurement settings were chosen randomly, and the measurements were completed so quickly that no signal, even travelling at the speed of light, could have passed between the 2 laboratories during the measurement process. The distance was large enough and the timing was tight enough to close the locality loophole, and because the diamond traps held the electrons reliably, essentially every entangled pair was successfully measured, closing the detection loophole. Nothing was thrown away, nothing was selectively ignored. The experiment ran for weeks, accumulating data from hundreds of successful entanglement events. The statistical analysis showed a clear violation of the Bell inequality. The probability that the result could have occurred by random chance, if local realism were true, was approximately 4% in the initial analysis and dropped further with additional data. It was the first time every major loophole had been closed in a single experiment using the same entangled pairs. The Bell inequality was violated. Quantum mechanics was right. Local realism was wrong. This was not a surprise to most physicists. The outcome had been anticipated for decades. But it mattered enormously that the test was finally done with no remaining escape routes. There was no longer any logically possible way for a locally realistic hidden variable theory to explain the results. The debate that began with the EPR paper in 1935 was settled experimentally 80 years later. Einstein's position, as reasonable and intuitive as it seemed, was ruled out by nature. In 2017, the experiment was pushed further using the Chinese satellite Mesius. Entangled photons were distributed to ground stations separated by more than 1,200 kilometers. The Bell inequality was violated at this enormous distance. In 2018, a team called the Big Bell test used random number choices generated by over 100,000 human volunteers around the world, each person mashing keys on a keyboard to produce random input. This addressed the freedom of choice loophole in the most dramatic way possible, replacing machine-generated random numbers with unpredictable human choices. The inequality was violated again, and in 2022, the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger for their experimental work with entangled photons. The Nobel Committee specifically cited their experiments establishing the violation of Bell inequalities and pioneering quantum information science. The work that began as a philosophical argument about the nature of reality had become one of the most celebrated achievements in experimental physics. So what exactly did Bell's theorem and its experimental confirmation tell us? Let me be very precise about this, because it is easy to overstate or misstate the conclusion. Bell's theorem does not say quantum mechanics is right. It is an experimental fact that quantum mechanics is right, but Bell's theorem itself is a statement about what local realism implies. The theorem says that if local realism is true, then certain correlations must stay below a specific ceiling. Experiments show the correlations exceed that ceiling. Therefore, local realism is false. This means at least one of the two assumptions must be wrong. Either locality is wrong, meaning distant events can somehow influence each other instantaneously, or realism is wrong, meaning particles do not have definite properties before measurement, or both are wrong. You cannot keep both. Most physicists accept that realism, at least in the naive classical sense, is what fails. Particles genuinely do not have definite polarizations before you measure them. The properties come into existence at the moment of measurement. This is not because the theory is incomplete, it is because that is how nature works. There is no deeper layer of hidden variables waiting to be discovered. The quantum description is the complete description. But this raises a deep puzzle about locality. If neither particle has a definite property before measurement, and if measuring one particle instantly determines what the distant particle will show, is that not a kind of non-local influence? Is something not travelling faster than light? This is one of the most subtle points in all of physics. The answer, according to the standard understanding, is no. Nothing is travelling. No signal is being sent. No energy or information is being transmitted faster than light. What happens is that the shared quantum state, which is a single mathematical object describing both particles, updates when a measurement is performed on either side. But this update does not carry usable information from one side to the other. Alice cannot use her measurement to send a message to Bob. She cannot control her outcome. She gets a random result. Bob gets a correlated random result, but neither of them learns anything about what the other did until they compare notes through an ordinary communication channel, which is limited by the speed of light. This distinction between correlation and communication is absolutely critical, and we will examine it much more carefully soon. For now, the key point is this. Bell's theorem killed the most natural classical explanation for entanglement. The particles are not carrying hidden instructions. The correlations are not coming from preset answers programmed at the source. Something genuinely new is happening. Something that does not fit into any classical framework of separate objects with independent properties. And this is what makes entanglement so remarkable. It is not just another quantum effect. It is the quantum effect that forces you to abandon the classical picture entirely. You can tolerate superposition by telling yourself it is just uncertainty. Maybe the particle does have a definite state and we just do not know it. You can tolerate the uncertainty principle by telling yourself it is just a limitation on measurement. Maybe the values exist, but we cannot access them simultaneously. These interpretive escapes are comfortable. They let you keep the classical worldview intact beneath a layer of quantum fuzziness. Entanglement closes those escapes. Bell's theorem proves mathematically that the comfortable classical picture cannot reproduce what entangled particles do. It is not a matter of interpretation. It is not a matter of taste. It is a mathematical fact confirmed by experiment. The classical worldview, where separate objects have separate definite properties and distant events are independent, is not a viable description of the physical world. This is why physicists talk about entanglement as one of the deepest features of quantum mechanics. It is not just that particles can be correlated. Classical particles can be correlated through common causes. It is that the correlations have a structure that no classical mechanism can produce. The shared quantum state generates something genuinely new, something without any classical precedent or classical explanation. And decades of increasingly precise experiments have confirmed that nature actually works this way. Einstein called entanglement spooky action at a distance. He meant it as a criticism, a sign that something was wrong with the theory. But the experiments showed that the spookiness is not in the theory, it is in nature. The universe really does exhibit these impossible-looking correlations between distant measurements. The theory was just honest enough to tell us so. What remains is to understand what entanglement actually means physically, what it allows and what it forbids, and why it matters so much for our understanding of reality. Because while the hidden variable escape is closed, the questions entanglement raises are far from settled. And the answers, as we will see, are both more subtle and more profound than either Einstein or Bohr imagined. Now, we need to be very careful, because everything we have covered so far, the strange correlations, the failure of hidden variables, the violation of Bell inequalities, all of it can very easily lead you to the wrong conclusion. And the wrong conclusion is the one you will find in almost every pop science article, every casual dinner conversation, and every breathless social media post about quantum physics. The wrong conclusion is this: entanglement lets particles communicate faster than light. It does not. And understanding why it does not is just as important as understanding why hidden variables fail. Because if you walk away from this story thinking entanglement is a faster-than-light telephone, you have not understood entanglement. You have replaced one misconception with another. You have traded the comfortable classical error for a dramatic science fiction error, and neither one captures what is actually going on. So let's be precise. Let's walk through exactly what happens when entangled particles are measured, step by step, and see why no information travels between them. This is where the physics becomes subtle, and where most popular explanations fall apart because they skip the crucial details. Alice and Bob share a pair of entangled photons. Alice has one, Bob has the other. They are far apart. Alice performs a measurement on her photon. She measures its polarization along the vertical axis. She gets a result. Let's say she gets vertical. Now, because the particles are entangled, she knows that if Bob measures along the same axis, he will get the corresponding result. She can predict Bob's outcome with certainty. Here is the question. Did Alice's measurement do something to Bob's photon? Did it change Bob's photon from an indefinite state to a definite one? Did some influence travel from Alice's detector to Bob's particle? In the mathematical formalism of quantum mechanics, the answer seems to be yes, in a certain sense. Before Alice's measurement, the shared quantum state described both photons as indefinite. After Alice's measurement, the state updates. If you ask quantum mechanics what Bob's photon is doing after Alice has measured hers, the answer is different from what it was before. Something changed in the description of Bob's particle, and that change happened at the moment Alice measured, regardless of how far away Bob is. This is what Einstein called spooky action at a distance. And at first glance, it really does look like faster-than-light influence. Alice does something here, and the quantum description of a distant particle changes there, instantly. But here is what that change actually amounts to in practice. Nothing, absolutely nothing that Bob can detect. Think about this from Bob's perspective. He is sitting at his detector, far away from Alice. He does not know whether Alice has measured her photon yet. He does not know what setting she chose. He does not know what result she got. All he has is his own photon arriving at his own detector. He measures it, he gets a result. Vertical or horizontal? Random, completely random. 50% chance of each. Now here is the critical point. Bob's result is exactly the same regardless of whether Alice has already measured her photon or not. If Alice measured first, Bob gets a random result. If Alice has not measured yet, Bob gets a random result. If Alice measured along a vertical axis, Bob gets a random result. If Alice measured along a horizontal axis, Bob gets a random result. If Alice decided not to measure at all and went to get coffee instead, Bob gets a random result. Bob's local statistics are completely unaffected by anything Alice does or does not do. This is not a technical detail, it is a theorem. It is called the no communication theorem, and it is a rigorous mathematical result within quantum mechanics. The theorem states that no measurement performed on one half of an entangled pair can produce any detectable change in the statistics observed at the other half. Alice cannot, by any choice of measurement or any sequence of measurements on her particle, alter what Bob sees when he measures his particle. His local results are always the same distribution, always the same probabilities, always the same randomness, regardless of Alice's actions. Let me say that again because it is so important. Looking at Bob's results alone, there is no experiment he can perform, no statistical test he can run, no pattern he can look for that will tell him whether Alice has measured her photon, what she measured, or what result she got. The information simply is not there. It is not hidden in his data. It does not exist in his local observations. Bob's half of the entangled pair carries no trace of Alice's actions. So where are the correlations? They are in the relationship between Alice's results and Bob's results. They appear only when Alice and Bob come together after the experiment and compare their lists of outcomes. When they lay their two lists side by side, they see the correlations. They see the matching. They see the patterns that no hidden variable theory can reproduce. But those patterns are invisible to either person alone. And comparing lists requires ordinary communication. Alice has to send Bob her list of results, or Bob has to send Alice his, or they both send their results to a third party. This communication travels at the speed of light or slower. It uses normal channels, radio signals, phone calls, emails, physical mail. Nothing exotic, nothing faster than light. The correlations are real, but you cannot access them without a classical communication channel, and that channel is limited by the speed of light, just like everything else in ordinary physics. This is why entanglement does not allow faster-than-light communication. The correlations exist, but they are useless for sending messages, because neither party can see them without the other party's data. Alice cannot encode a message in her results because she cannot control her results. She gets random outcomes. She cannot choose to get vertical instead of horizontal. The quantum randomness is genuine and uncontrollable. And Bob cannot decode a message from his results because his results carry no information about Alice's choices. His data is pure noise, indistinguishable from what he would see if his photon were not entangled at all. Let me illustrate this with a specific scenario to make it absolutely concrete. Suppose Alice wants to send Bob a message using entanglement. She has an idea. She will measure her photon to send a 1, and she will not measure it to send a 0. She figures that measuring her photon collapses the entangled state, and not measuring it leaves it intact. Maybe Bob can tell the difference, but he cannot. If Alice measures, Bob gets a random result. If Alice does not measure, Bob still gets a random result. His photon arrives at his detector and produces an outcome either way. The probability distribution of his outcomes is identical in both cases, 50% vertical, 50% horizontal, regardless of what Alice did. There is no signal, there is no message. There is just randomness on both ends that happens to be secretly correlated in a way that only becomes visible when you combine the two datasets, through ordinary communication. Suppose Alice tries a different strategy. Instead of choosing whether to measure, she tries choosing what to measure. She switches between measuring vertical polarization and measuring at 45 degrees, hoping that her choice of setting will leave some statistical fingerprint on Bob's results. But the no communication theorem covers this too. No matter what basis Alice selects, no matter how she varies her measurements from one photon to the next, Bob's results remain the same distribution. 50% one outcome, 50% the other. Pure randomness. His statistics are completely insensitive to her choices. She can switch settings frantically, follow elaborate patterns, use a random number generator, or measure every photon identically. Nothing she does produces any detectable change on Bob's side. The wall between them is absolute. Alice's choices are invisible in Bob's data, and the correlations that entanglement creates remain locked away until the two of them exchange their results through an ordinary channel that respects the speed of light. This is what makes entanglement so fascinating and so frustrating at the same time. It produces correlations that are genuinely non-classical, genuinely inexplicable by any model of separate objects carrying independent properties. But it wraps those correlations in a shell of local randomness that prevents them from being used for signaling. The universe gives you something extraordinary with one hand and takes away the most obvious application with the other. Some people hear this and ask, but is there really no way? What if Alice is cleverer about her measurements? What if she uses a different basis? What if she measures multiple properties? What if she uses a whole sequence of entangled pairs in some intricate pattern? The answer is still no. The no communication theorem is not a practical limitation. It is not something you can work around with better technology or smarter protocols. It is a mathematical consequence of the structure of quantum mechanics itself. As long as quantum mechanics is correct, and every experiment ever performed confirms that it is, entanglement cannot be used to send information faster than light. Period. This has been proven rigorously, not just argued informally. It follows from the mathematical properties of quantum states and quantum measurements. No cleverness can defeat a theorem. This is also the right moment to address some of the more extravagant claims you encounter in popular culture. Because entanglement has become a magnet for mysticism and exaggeration, and the gap between what entanglement actually is and what people think it is has grown enormous. Entanglement is not telepathy. It does not allow minds to communicate across distances. It does not mean that everything in the universe is connected in some mystical web of consciousness. It does not validate New Age claims about human thought influencing distant physical reality. It does not mean that observing something here changes something there in a way that matters for your daily life. These claims take a real, precisely defined physical phenomenon and inflate it beyond all recognition. Entanglement is not even spooky in the way the word is usually meant. It is surprising. It challenges classical intuitions. It tells us that the universe has a deeper structure than our everyday experience reveals. But it is a well-understood, mathematically precise, experimentally confirmed aspect of quantum mechanics. It is not mysterious in the sense of being unexplained. It is mysterious only in the sense that it contradicts the mental model of reality most people carry around, a model that was never correct at the quantum level to begin with. So what is entanglement physically? What does the shared quantum state actually mean? Let me try to describe it as carefully as I can without resorting to the mathematics, which is where the full precision lives. When two particles are entangled, the system they form has properties that cannot be reduced to properties of the individual particles. This is not like two billiard balls, where you can describe each ball's position and velocity independently, and then talk about the pair as the combination of two individual descriptions. In entanglement, the pair has a definite quantum state, but the individuals do not. The whole is not the sum of its parts. The whole has a precise description, and from that description you can extract everything you need to predict the outcomes of any experiment on the pair. But you cannot assign each particle its own separate complete description. This is technically called non-separability. The quantum state of the pair is non-separable. It cannot be factored into a product of two individual states, one for each particle. If you try to describe one particle in isolation, ignoring the other, you lose information. Not because you're being careless, but because the information genuinely does not reside in either particle individually. It resides in the relationship between them. Here is an analogy that captures part of this, though, like all analogies for quantum mechanics, it is imperfect. Imagine a book written in a code where individual letters are meaningless. The letter A by itself carries no information. The letter G by itself carries no information. But the pair AG together means something specific. The meaning is not in either letter. It is in the combination. You could study individual letters for years and learn nothing. The information is relational. It lives in the pairing. Entanglement is something like this, but stranger, because in the quantum case, the individual particles do not even have definite states to examine. It is not that each particle has a letter and the meaning is in the combination. It is that neither particle has a definite letter at all until you measure it. Before measurement, each particle is in a genuine superposition of possibilities. But the shared quantum state guarantees that when you do measure both, the results will be correlated in a specific, precise way. The indefiniteness is shared. It is not that each particle is individually uncertain and the uncertainties happen to match. It is that there is a single uncertainty encompassing both particles simultaneously. One shared cloud of possibility for the pair, not two separate clouds that happen to overlap. This is what makes entanglement fundamentally different from any classical correlation. Classical correlations always decompose into properties of the individual objects. If two classical objects are correlated, it is because each one carries some property, maybe hidden, maybe unknown, but a definite property that determines its behavior. Quantum entanglement cannot be decomposed this way. The Bell inequality violation proves it. The correlations exceed what any decomposition into individual properties could produce. The wholeness is irreducible. Now, let me address one more thing that gets badly misrepresented in popular accounts: quantum teleportation. This is a real protocol. It has been demonstrated experimentally, and its name is extremely misleading. Quantum teleportation does not teleport matter. It does not teleport energy. It does not move physical objects from one place to another. It does not disassemble something here and reassemble it there. And it absolutely does not work faster than light. What quantum teleportation actually does is transfer a quantum state from one particle to another, using entanglement and classical communication working together. Here is how it works in simplified terms. Alice has a particle in some quantum state she wants to transfer to Bob. She does not know what the state is. She cannot measure it because measuring it would destroy it. She just has a particle in an unknown state, and she wants Bob to end up with a particle in the same state. Alice and Bob share a pair of entangled particles. Alice performs a special kind of joint measurement on her unknown state particle and her half of the entangled pair. This measurement gives her one of 4 possible outcomes, each equally likely. She sends her result to Bob through an ordinary classical channel: a phone call, a text message, an email. This communication travels at the speed of light, or slower. When Bob receives Alice's message, he knows which of 4 possible operations to perform on his half of the entangled pair. He performs the appropriate operation, and his particle ends up in exactly the quantum state that Alice's original particle was in. The state has been transferred, not copied, because the original is destroyed in the process. Transferred. The quantum state that was here is now there. But notice what happened. Alice had to send Bob a classical message, 2 bits of ordinary information. Without that message, Bob's particle is in a random state. He cannot reconstruct Alice's quantum state without Alice's classical communication telling him which operation to apply. The protocol requires a classical channel, and that channel is limited by the speed of light. So quantum teleportation, despite its dramatic name, does not transmit anything faster than light. It is a clever protocol that uses entanglement as a resource, combined with classical communication, to transfer quantum information in a way that would otherwise be impossible. The protocol was proposed in 1993 by Charles Bennett, Gilles Brasseur, and 4 other physicists. It was first demonstrated experimentally in 1997 by Anton Sillinger's group using entangled photons. Since then, it has been performed many times with increasing sophistication, including over satellite links using the Messias satellite, achieving quantum teleportation over distances of more than 1,400 kilometers. Quantum teleportation is real, important, and genuinely useful for quantum information science, but it is not what science fiction means by teleportation. You cannot teleport a person. You cannot teleport an object. You are transferring a quantum state, an abstract mathematical description, not physical matter. And you need ordinary communication to make it work. The speed of light limit is completely respected. There is one more misconception worth addressing directly, and it is perhaps the most common one of all. Many people hear about entanglement and conclude that it means measurement on one particle instantly affects the other particle, that Alice measuring her photon does something to Bob's photon, that the distant particle changes when the local particle is measured. This language is not exactly wrong, but it is dangerously misleading. In the mathematical formalism of quantum mechanics, yes, the description of the total system updates when a measurement is performed on one part. But this update has no local physical consequences for the distant particle. It produces no observable change. It generates no detectable effect. It is what physicists sometimes call a change in our knowledge, rather than a change in physical reality, although even that language is contested, because quantum mechanics blurs the boundary between knowledge and reality in ways that remain philosophically unresolved. The safest and most accurate way to think about it is this. Before measurement, the two particles share a quantum state that is non-separable. After measurement on one particle, the shared state is gone. Each particle now has its own individual state, but nothing travelled between them. No force was exerted, no signal was sent. The transition from shared state to individual states is not a physical process in the ordinary sense. It is not like a wave propagating through space or a ball rolling downhill. It is a change in the quantum description of the system that has no spatio-temporal character. It does not happen at a particular speed. It does not propagate through space. It is not the kind of thing you can intercept or block or observe in transit, because it is not in transit. There is nothing travelling. This is deeply counterintuitive. We are used to thinking that if something here and something there are correlated, then either they were programmed together in the past or something connects them now. Entanglement says there is a third option. Two particles can be described by a single shared state that is neither a signal travelling between them nor a set of hidden instructions they carry independently. It is something genuinely new, something the classical world does not contain, something that exists in the quantum formalism and manifests in experimental correlations, but does not map onto any familiar picture of influences travelling through space. And this is perhaps the deepest lesson of entanglement for our understanding of what it is and what it is not. Entanglement is not a connection between the particles in the usual sense of the word connection. There is no thread linking them. There is no channel between them. There is no field stretching from one to the other. Instead, there is a single quantum state that describes the pair as a unit. The pair has properties. The individuals do not. And when you measure one individual and force it to have a definite property, the shared state that tied them together is consumed. The pair becomes two separate individuals. The correlations are revealed when you compare the results, and nothing had to travel between the particles for any of this to happen. This is what makes entanglement simultaneously more mundane and more profound than the popular image suggests. More mundane because it does not enable faster-than-light communication, does not validate telepathy, does not connect everything to everything in some mystical web. More profound because it tells us that the quantum world is not built from independent pieces assembled together. It is built from wholes that cannot be decomposed into parts. The separateness that we take for granted, the idea that distinct objects in distinct places have distinct properties, is not a fundamental feature of reality. It is an approximation. A very good approximation at everyday scales where quantum effects are negligible, but an approximation that fails at the fundamental level, where entanglement reveals a deeper wholeness that no classical picture can capture. And this deeper wholeness is not a vague philosophical claim, it is a precise, experimentally confirmed, mathematically rigorous feature of quantum mechanics. The Bell inequality violations prove that the correlations cannot come from separate individual properties. The no communication theorem proves that the correlations cannot be used for signaling. Both results together paint a picture of a universe that is neither classically local in the way Einstein wanted, nor non-locally communicating in the way science fiction imagines. It is something else entirely, something that requires genuinely new concepts to describe, something that our classical language and classical intuitions are simply not equipped to capture. Entanglement exists. It is real. It has been measured. It violates classical limits. It does not send signals. And it tells us that the universe, at its most fundamental level, is not made of separate, independent parts. What it is made of, and what that means for our understanding of physical reality, is the question we turn to now. So, where does all of this leave us? We know entangled particles produce correlations that no classical model of independent objects can reproduce. We know no signal travels between them. We know the correlations are real, confirmed by decades of experiments, with every loophole closed. And we know the shared quantum state that describes entangled particles cannot be broken into separate descriptions for each particle individually. The wholeness is irreducible. But saying what entanglement is not signaling, not hidden variables, not telepathy, only takes you so far. The deeper question remains: what does entanglement tell us about the nature of physical reality? What kind of universe produces these correlations? What must be true about the world for entanglement to work the way it does? This is where we run into one of the most profound challenges in the history of science. Because the experimental facts are clear, but their interpretation is not. Physicists agree completely on the mathematics and the predictions. They agree on what will happen in every experiment, but they disagree, sometimes passionately, on what the mathematics means. What story the equations are telling about the physical world behind the measurements. The issue centers on a concept called local realism. We touched on this earlier, but now we need to examine it closely, because understanding why entanglement challenges local realism is understanding why entanglement challenges reality itself. Remember the two assumptions behind Bell's inequality. Realism, that particles carry definite properties whether or not anyone checks, and locality, so that nothing Alice does can instantaneously affect Bob's distant particle. Together they form local realism, the classical expectation that separate objects behave separately and possess independent attributes. Bell's theorem forced us to abandon at least one piece. The experiments confirmed it. But which piece do you give up? And what does the universe look like once you do? This is where the real difficulty begins, because each option leads somewhere uncomfortable. Together, realism and locality form the worldview that virtually every human being carries through daily life. Objects have definite properties. Distant events are independent unless connected by some physical process moving through space. This is the framework that classical physics operates within. It is the framework that general relativity operates within. It is the framework that every technology you use, every bridge you cross, every airplane you fly in, was designed within. And it works. It works spectacularly well for everything at human scales and above. But Bell's theorem proved that local realism cannot reproduce the correlations produced by entangled particles. The experimental violations of Bell inequalities confirmed this. Nature does not obey local realism. At least one of the two pieces must be abandoned. This is not a minor technical adjustment. This is a crisis for our picture of physical reality. Because both locality and realism seem indispensable, giving up either one has consequences that are deeply uncomfortable. Suppose you give up realism. You accept that particles do not have definite properties before measurement. Then the quantum description is complete. There are no hidden variables. Particles exist in superpositions of possibilities until measurement forces a definite outcome. This is the standard interpretation of quantum mechanics, often associated with Niels Bohr and the Copenhagen school of thought. It works. The predictions are correct. But it raises disturbing questions. What counts as a measurement? When exactly does the superposition collapse into a definite outcome? Is it when a detector clicks? When a human observes the detector? When the result is recorded? The measurement problem, as it is called, has never been fully resolved within this interpretation. There is no precise physical criterion for when collapse happens. It is simply postulated to occur. And there is a deeper issue. If particles do not have definite properties before measurement, what are they? What kind of thing exists in a superposition? Is the quantum state a description of reality, or a description of our knowledge of reality? If it is a description of reality, then reality itself is indefinite, fuzzy, uncommitted to particular values until observation forces its hand. That is a radical ontological claim. If the quantum state is a description of knowledge, then whose knowledge? And what is the underlying reality that the knowledge is about? Suppose instead you give up locality. You accept that particles have definite properties. They are real objects with real attributes, but you allow instantaneous influences between distant systems. This is the approach taken by David Bohm's pilot wave theory, sometimes called Bohmian mechanics, or the de Broglie-Bohm theory. In this picture, particles always have definite positions and follow definite trajectories, but they are guided by a quantum wave function that can connect distant particles instantaneously. When Alice measures her particle, the pilot wave updates everywhere at once, instantaneously determining what Bob's particle will do. Bohm's theory reproduces all the predictions of standard quantum mechanics. Every experiment comes out the same way. It is a fully deterministic, fully realistic theory. Particles have definite properties at all times. There are no measurement problems and no collapses. But the price is non-locality. The pilot wave connects distant particles in a way that explicitly violates the spirit of Einstein's relativity, which says nothing should influence distant events instantaneously. Bohm's theory does not allow faster-than-light signaling, so it does not technically contradict relativity's prohibition on superluminal information transfer. But it does require a kind of instantaneous connection between distant particles that most physicists find deeply uncomfortable. There is a third option, perhaps the most radical of all. You can keep both realism and locality, but you pay an enormous price. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that every quantum measurement causes the universe to split into multiple branches. When Alice measures her entangled photon and gets vertical, there is also a branch of reality where she got horizontal. Both outcomes occur. Both are real. The universe splits, and in each branch, the correlations work out consistently without any need for non-local influences or collapse. In Alice's branch where she got vertical, Bob's branch also shows the correlated result. In the other branch, the other results appear. Everything is local, everything is real, and the Bell inequality is satisfied within each branch because the correlations arise from the branching structure of reality rather than from influences between particles. The price is ontological extravagance. The many worlds interpretation requires an ever-branching tree of parallel realities, each as real as the one you experience. Every quantum event, everywhere in the universe, at every moment, creates new branches. The number of branches is incomprehensibly vast. You cannot observe the other branches. You cannot communicate with them. You cannot verify their existence. Whether this counts as a virtue of the theory, it explains everything without collapse or non-locality, or a vice, it postulates an infinity of unobservable realities, depends on your philosophical temperament. To make the stakes of this debate concrete, imagine Alice measuring her entangled photon and getting vertical. What physically happened according to each interpretation? In the Copenhagen interpretation, Alice's measurement caused the shared quantum state to collapse. Before she measured, neither photon had a definite polarization. The moment her detector clicked, the superposition vanished. Her photon became vertical. Bob's photon, wherever it is, instantaneously acquired the corresponding definite state. Nothing traveled between them. The collapse is not a physical process propagating through space. It is a sudden, discontinuous update of the quantum state that has no mechanism and no explanation beyond the postulate that measurements produce definite outcomes. The universe simply jumped from indefinite to definite, and the theory does not say how or why. In Bohm's pilot wave theory, both photons had definite polarizations at every moment. They were always somewhere specific, doing something specific, but their behavior was guided by a pilot wave, the quantum wave function, which connected them non-locally. When Alice's measurement occurred, the pilot wave instantaneously adjusted everywhere, including at Bob's distant location. Bob's particle changed its trajectory in response, not because a signal was sent, but because the pilot wave is a global object that updates as a whole. The determinism is complete. The realism is preserved. Every particle has definite properties at all times. But the pilot wave's instantaneous global updating means the theory is explicitly non-local. There is a real connection between distant particles, just not one that can be used to send messages. In the many worlds interpretation, Alice's measurement did not produce a single outcome. It produced all outcomes simultaneously. The universe branched. In one branch, Alice got vertical and Bob's particle entered the corresponding branch. In another branch, Alice got horizontal and Bob's particle entered that corresponding branch. No collapse occurred. No non-local influence occurred. The wave function never collapsed because it never needed to. It simply kept evolving according to the standard quantum equations, and what looks like a single outcome to Alice is actually Alice splitting into multiple copies, each seeing a different result, each unaware of the others. The correlations between Alice and Bob are maintained because the branching is consistent. The branch where Alice got vertical is the same branch where Bob gets the correlated outcome. They share a branch, not a signal. Each of these pictures is internally consistent. Each reproduces every experimental prediction, and each paints a radically different portrait of what is really happening. The universe either collapses without explanation, or it is guided by an invisible, non-local wave, or it splits into countless copies of itself every time a quantum event occurs. The experimental evidence cannot distinguish between them. The choice, for now, is philosophical. These are not the only interpretations. There are relational interpretations, where quantum states are defined relative to observers. There are information-theoretic interpretations, where the quantum state represents information rather than physical reality. There are collapse theories that modify the equations of quantum mechanics slightly, adding a physical mechanism for collapse that makes it a real process happening at a specific rate. Each interpretation handles entanglement differently. Each makes the same experimental predictions, and each tells a different story about what the universe is really like. The fact that multiple incompatible interpretations all reproduce the same predictions is itself deeply significant. It means the experimental evidence does not uniquely determine the picture of reality. The math tells you what will happen. It does not tell you what is happening. This is unusual in science. In most of physics, the successful theory tells you both what to predict and what to believe about the underlying reality. Quantum mechanics, at least when it comes to entanglement, separates the two. The predictions are settled, the reality is not. But regardless of which interpretation you prefer, certain conclusions are unavoidable. Entanglement shows that this non-separability has measurable consequences that no revision of the classical picture can absorb. Systems that have interacted and become entangled carry shared quantum states whose correlations exceed every classical bound we can construct. This is not a feature of our description. It is a feature of what the description successfully describes. The correlations are real. The non-separability is real. Whatever the correct interpretation turns out to be, it must accommodate the fact that entangled particles are not fully separate things. This has practical consequences. Entanglement is not just a philosophical puzzle, it is a physical resource. Over the past few decades, physicists and engineers have learned to harness entanglement for tasks that are impossible with classical physics alone. And these applications are not speculative. They are being built and tested right now. The first major application is quantum cryptography. Classical encryption, the kind that protects your bank transactions and your private messages, relies on mathematical problems that are hard to solve. The RSA encryption system, for example, is based on the difficulty of factoring large numbers into their prime components. If you multiply two large prime numbers together, the result is easy to compute. But if someone gives you the result and asks you to find the original primes, the problem is enormously difficult for classical computers. This difficulty is what keeps your data safe. But it is not physical security, it is computational security. The encryption is safe only because no one has a fast enough algorithm to break it. If someone built a sufficiently powerful computer or discovered a clever algorithm, the encryption would fall. And in 1994, Peter Shaw showed that a quantum computer, a computer that operates on quantum principles using qubits instead of classical bits, could factor large numbers exponentially faster than any known classical algorithm. A sufficiently large quantum computer running Shaw's algorithm could break RSA encryption. We do not have such a computer yet, but the theoretical possibility is established, and quantum computers are advancing steadily. Quantum cryptography offers a solution. Using entanglement, two parties can establish a shared secret key with security guaranteed by the laws of physics, rather than the difficulty of a math problem. The basic idea goes back to a protocol called BB84, proposed by Charles Bennett and Zeel Brassar in 1984, which uses quantum states but not entanglement directly. Later protocols use entangled pairs explicitly. Alice and Bob share entangled photons. They each measure their photons along randomly chosen axes. They then publicly compare which axes they used, but not their results. For the cases where they happen to choose the same axis, their results are perfectly correlated, giving them a shared string of random bits that no eavesdropper can know. Why is this secure? Because of a fundamental property of quantum mechanics. You cannot measure a quantum state without disturbing it. If an eavesdropper tries to intercept and measure the photons, the act of measurement changes the quantum states. This introduces errors into the correlations between Alice and Bob. They can detect the eavesdropper's presence by checking a subset of their results for discrepancies. If the error rate is too high, they know someone is listening and they discard the key. If the error rate is low, they know the key is secure, not because eavesdropping is technologically difficult, but because physics forbids undetectable eavesdropping. The security comes from the laws of nature, not from computational assumptions. Quantum key distribution has been demonstrated over optical fibers spanning hundreds of kilometers and over satellite links spanning over 1,000 kilometers using the MESIA satellite. Commercial systems are already available. Several countries are building quantum communication networks. This is not future technology. It is present technology made possible by our understanding of entanglement. The second major application is quantum computing. A classical computer stores information in bits, each of which is either 0 or 1. A quantum computer stores information in qubits, which can be in superpositions of 0 and 1 simultaneously. When multiple qubits are entangled, the system can explore an exponentially large space of possibilities in parallel. This does not mean a quantum computer tries all answers at once, which is an oversimplification you often hear. What it means is that quantum interference, the ability of quantum amplitudes to add constructively or destructively, can be harnessed to make certain computations dramatically more efficient. Entanglement is the resource that makes quantum computing powerful. Without entanglement, qubits are just classical bits in disguise. A quantum computer whose qubits are never entangled can always be simulated efficiently by a classical computer. It is entanglement that creates the computational advantage. The shared quantum states between multiple qubits allow the computer to represent and manipulate information in ways that have no classical counterpart. Quantum computers are still in their early stages. The largest current machines have a few thousand qubits, and they are noisy, meaning their quantum states degrade quickly due to interactions with their environment, a process called decoherence. Building a large, error-corrected quantum computer that can solve problems beyond any classical computer's reach is one of the great engineering challenges of our time. But progress is steady, and the theoretical foundations, built on our understanding of entanglement, are solid. There is a third area where entanglement has proven transformative, and it is less well known, but arguably more profound. Entanglement has become a central concept in our understanding of space-time itself. Over the past 2 decades, theoretical physicists have discovered deep connections between quantum entanglement and the geometry of space. These connections suggest that space-time, the fabric of the universe described by Einstein's general relativity, might not be fundamental. It might emerge from patterns of quantum entanglement at a deeper level. This idea, which grows out of work on the holographic principle and certain models in string theory, proposes that the spatial distance between 2 points might be determined by the amount of entanglement between the quantum degrees of freedom associated with those points. More entanglement means shorter distance. Less entanglement means greater distance. If you remove entanglement entirely between 2 regions, they become disconnected, no longer part of the same space. If this picture is correct, then entanglement is not just a strange feature of quantum particles, it is the glue that holds space together. The very existence of space as a connected, continuous arena might depend on entanglement between the quantum degrees of freedom from which space-time emerges. This is speculative. These ideas are at the frontier of theoretical physics, and we do not yet have experimental confirmation. But the mathematical structures are compelling, and they suggest that entanglement may be far more fundamental than anyone initially imagined. Not just a curiosity of quantum mechanics, but a key to understanding the deepest structure of reality. This line of thinking was crystallized in 2013 by physicists Juan Maldacena and Leonard Susskind in a conjecture known by its shorthand ER equals EPR. The letters on the left stand for Einstein and Rosen, who in 1935 described theoretical bridges connecting distant regions of spacetime. These bridges are what we now call wormholes. The letters on the right stand for Einstein, Podolsky, and Rosen, the same trio who, in the same year, described quantum entanglement. The conjecture proposes that these two phenomena, discovered in the same year by overlapping groups of physicists, are actually the same thing described in different languages. A wormhole is a geometric connection between distant points in spacetime. Entanglement is a quantum connection between distant particles. The ER equals EPR conjecture says these are not merely analogous, they are identical. Every pair of entangled particles is connected by a tiny microscopic wormhole, and every wormhole, even the large traversable ones imagined in science fiction, is a manifestation of entanglement between the quantum degrees of freedom on either side. If this is correct, the implications are extraordinary. It means that when you entangle two particles, you are not just creating a strange quantum correlation, you are creating a tiny bridge in the geometry of space-time. When you destroy entanglement between two regions, you are tearing space apart. Space-time connectivity, the very fact that one point in space is next to another point in space, might be a consequence of entanglement holding those points together. Physicists have tested this idea in simplified mathematical models, particularly in a framework called anti-de Sitter space, which is a curved space-time used as a theoretical laboratory. In these models, the connection between entanglement and geometry is precise and quantitative. You can calculate how much entanglement is needed between two regions to produce a given spatial distance between them. If you reduce the entanglement, the distance increases. If you remove it entirely, the regions disconnect. Space falls apart. These are mathematical results in simplified models, not direct descriptions of our universe. Our universe has different geometry than anti-de Sitter space, but the mathematical structures are suggestive enough that many physicists believe something similar holds in the real world. If it does, then entanglement is not just one feature of quantum mechanics among many. It is the feature from which space-time itself is constructed. The fabric of the universe, the arena in which everything happens, might be woven from quantum correlations between systems that, viewed individually, have no definite properties at all. Let's step back now and consider what we have learned over the course of this entire journey. We started with a simple question. How can two distant particles behave in a coordinated way without any signal between them and without carrying preset instructions? The answer, which quantum mechanics provides and experiments confirm, is that the particles are described by a single shared quantum state. This state is non-separable. It cannot be decomposed into individual states for each particle. The correlations it produces exceed what any classical model of independent objects can generate. Bell's theorem proved this mathematically. Experiments confirmed it physically. And the no-communication theorem ensures that the correlations cannot be exploited to send messages faster than light. The implication is that the universe is not built from independent parts in the way our everyday experience suggests. At the quantum level, systems that have interacted can remain connected through shared states that resist any classical description. This connection is not a signal. It is not a force. It is not a physical link stretching through space. It is a feature of the quantum state itself, a mathematical object that describes the system as a whole and cannot be reduced to descriptions of its components. This challenges local realism, the common sense framework that objects have definite properties independently of observation, and that distant events cannot influence each other instantaneously. Bell's theorem forces us to abandon at least part of this framework. Whether we give up realism, accepting that particles do not have definite properties before measurement, or give up locality, accepting some form of instantaneous connection between distant systems, or adopt an entirely different ontology, like the many worlds interpretation, the classical picture of a universe made of separate independent things with separate independent properties is not viable. And this matters. Not just for physics, not just for philosophy, but for what kind of universe we live in. The separateness that feels so obvious, the conviction that this thing here and that thing there are genuinely distinct, genuinely independent, genuinely unrelated unless connected by some visible mechanism, that conviction is an approximation. It is an extremely good approximation at human scales, where quantum effects are negligible and classical physics works beautifully. But it is not the final truth. At the deepest level, the universe has a holistic structure that classical physics cannot capture. This does not mean everything is connected in some vague, mystical sense. The connections are specific, precise, mathematically described, and experimentally measurable. They involve specific particles that have interacted in specific ways, producing specific shared states with specific correlations. Entanglement is not a blanket claim that everything affects everything else. It is a precise claim about particular systems prepared in particular ways. The universe is not a fuzzy web of universal connection. It is a precisely structured quantum system in which certain subsystems share states that resist classical decomposition. But even stated precisely, the implication is staggering. The universe, at bottom, does not consist of separate things. It consists of relationships between things, correlations between measurements, shared states that belong to no single particle, but to pairs and groups, and ultimately to the whole. The parts are not primary. The whole is primary, and the parts emerge from the whole through the process of measurement and interaction, not the other way around. Einstein spent the last 3 decades of his life arguing against this picture. He believed passionately in a universe of separate real objects with definite properties, evolving through local causal processes. He believed quantum mechanics must be incomplete, that hidden variables must exist, that the strange correlations of entanglement must have a classical explanation. He was motivated not by stubbornness, but by a deep physical intuition that had served him brilliantly throughout his career. That same intuition that led him to special relativity, general relativity, and the photoelectric effect told him the quantum picture must be wrong. But on this question, his intuition failed. Nature sided with quantum mechanics. The hidden variables do not exist. The classical picture does not work. The correlations are exactly as quantum mechanics predicts, and no locally realistic theory can reproduce them. Einstein was wrong, not because he was careless or confused, but because the universe turned out to be stranger than even one of the greatest minds in human history could accept. And perhaps that is the most important lesson of all. Our intuitions about reality were built by evolution to help us survive in a world of medium-sized objects moving at moderate speeds. They were never designed to accurately represent the quantum world. They were designed to help us find food, avoid predators, and navigate social groups. The fact that these intuitions fail at the quantum level is not a flaw in quantum mechanics. It is a limitation of human cognition. Entanglement does not look impossible because something is wrong with the physics. It looks impossible because something is wrong with our expectations. Our expectations were shaped by a world where entanglement is invisible, where quantum effects average out, where the classical approximation works perfectly. We built our picture of reality from that limited experience, and then we discovered that the experience was not the whole story. The universe is not obligated to match our intuitions. It is not obligated to be visualizable or comfortable or familiar. It is obligated only to be consistent with itself, and it is. Quantum mechanics is one of the most precisely tested theories in the history of science. Its predictions have been confirmed to extraordinary accuracy across an enormous range of phenomena. Entanglement, strange as it seems, is part of a theory that works. And sometimes, the most important thing a scientific discovery can do is show us that the world is not what we thought it was. Entanglement shows us that separateness is not fundamental, that the universe, at its deepest level, has a wholeness that cannot be decomposed into independent parts, that the correlations between distant measurements are not carried by signals or instructions, but are woven into the quantum state of the universe itself. This is not mysticism, it is physics, measured, confirmed, and precise. And physicists are only beginning to understand how far its consequences reach. Think about what it means to live in such a universe. You walk through your daily life surrounded by objects that seem solid, separate, independent. The table is here. The chair is there. They have nothing to do with each other. You are here. The person across the room is there. You are separate beings in separate locations with separate experiences. This is so obviously true that questioning it feels absurd. But at the level of fundamental physics, this separateness is not built in. It is built up. It emerges from a deeper layer where the concept of separate objects in separate places does not apply in the way we assume. Entanglement is the proof. Two particles, created together and sent to opposite ends of a laboratory or opposite sides of a continent, remain part of a single quantum whole. They do not have independent identities. They do not have separate stories. They have one shared story that only looks like two separate stories when you examine each particle in isolation and ignore the other. And this is not limited to specially prepared laboratory particles. Entanglement is everywhere. Every interaction between quantum systems can create entanglement. Atoms in a solid are entangled with their neighbors. Photons from the early universe are entangled with matter they scattered off billions of years ago. The particles in your body were forged in stars and have interacted with countless other particles over billions of years. The web of entanglement stretching across the universe is inconceivably vast, though almost none of it produces correlations organized enough to detect or exploit. It is the background texture of quantum reality, invisible at human scales, but present everywhere. This does not mean you are psychically linked to distant stars or that your thoughts influence faraway galaxies. The no communication theorem is absolute. The correlations are real but inaccessible without classical communication. The wholeness is genuine but not mystical. It is physical, mathematical, precise. It means that the universe, at bottom, is a single quantum system whose parts are more intimately related than any classical picture allows. And we, made of quantum particles ourselves, are part of that system, not separate from it, not observers looking in from outside, part of it. Participants in a quantum universe that does not draw sharp boundaries between here and there, between this system and that one, between observer and observed, in the way we instinctively assume. Entanglement began as a puzzle. Einstein raised it as an objection to quantum mechanics. Bell turned it into a testable question. Experimentalists answered that question decisively. And now, decades later, entanglement has become one of the most important concepts in all of physics. It secures communications. It powers new kinds of computation. It may explain the origin of space-time itself, and it tells us something deep and humbling about the nature of the universe we inhabit. The universe is not a collection of separate things. It is a web of relationships. The parts do not come first and then interact. The relationships come first, and the parts emerge from them. This is what entanglement teaches, not as metaphor, not as poetry, as physics, tested, confirmed, and precise. And it is, arguably, the most profound single fact we have ever learned about the world.